Hello everyone. Today is the 43rd day of Leetcode 75 challenge. Let's begin with the 43rd question. Question 841. Keys and room. The level of the problem is medium. I will request you to read the question beforehand as I will deep dive into the PPT and explain it in simpler way. Now let's understand the problem in the easiest way possible. So you are given a list of rooms and each room is represented by a list of keys. Fine. So basically they're telling you that you have a room and it has keys in that. Okay. Each key is labeled with an integer that corresponds to another room number. Okay, you can start from room 0, which is already unlocked. Your task is to determine if you can visit all the rooms by collecting and using keys as you explore. So basically, you are given the rooms and each have a key. So this key is an integer to the another room. Okay, so this key unlocks some other room in the pathway. As you enter a room, you may find new keys that allow you to access more locked rooms. So this is the thing which I said right now. The final output should be true if all rooms can be visited using the keys we collected, or false if some room remains inaccessible. So basically, if there are multiple rooms and we are able to access all the rooms provided the keys in it, suppose this key in the first room or room number 0 has key with integer value 1. So it can unlock room number 1 and it has key 2 which can unlock the room number 2. If so, if we don't have any key which unlocks room number 2, for example, and this room is left out, so in that case we will return false because we were not able to access all the rooms. So I hope you understood the problem explanation. It is pretty straightforward and simple. Now let's look at the constraints. N is equals to room's length, and n value could be from 2 to 1000, and value of each of the rooms of I could be from 0 to 1000, and the sum of the length of this particular thing, rooms of I, would be between 1 to 3000, and rooms of I of j will be from 0 to n, and all the values of the room of I are unique. So there is no there are no keys which are similar like 2 2 and 2, or 2 2 and 2, right? It has to be 1 2 and 3, all are unique. Fine. I hope you understood the problem explanation. It was pretty easy. Now let's move to the next slide. Let's understand the input output of the problem. Suppose you are given this, okay? So let me write it here. What it basically states is that, okay, so this is there. So this is room 0, room 1, room 2, okay, and room 3. Okay, so here we can see that, suppose room 0 is this one, fine. It has key 1 in it. So which means that at room 0 you have the key value 1, so you could access the room number 1. So this is room number 1. It has key 2. So that means that from 1 to 2 you could go. Okay. At room number 1 you have key of room number 2, which is this one, right? So you could go from room number 1 to room number 2. Okay. Which has the key value as 3. Okay. It has key value 3, which means that it can go to room 3. Okay. And key 3 does not have anything. So it stops here. So you could understand that this particular thing is the room, and within that is the key. So this is what we got, and we visited all the nodes, or we could say all the rooms having the keys. Fine. Now let's try this particular example. Here, if you could see, let it be room 0, let it be room 1, room 2, and room 3. Fine. So if you're standing at room 0, let it be room 0. Okay, note, okay, and it has key of 1 and 3 room number. Okay, which means that you could go to room number 1 and you could go to room number 3. Okay, let's check. For room number 1, you have key as 3 in it and 0 and 1. Okay, so that means that from room number 1, you could go to room 0 also, and it goes to itself. So that is not necessary to draw, but yeah, I have drawn it. And after that, it has to key value to room number 3 also. Fine. At room number 2, this is the room number 2. It has the key to room number 2 itself. So it's basically a self loop, right? So in room number 2, you have the key of room number 2 itself. So that means you cannot go to any other rooms. Okay. At room number 3, you have the key to room number 0. So you could see that in this particular example, you are not able to visit all the rooms given because room number two does not have any keys to any other room. Neither the other rooms have keys to enter room number two. So therefore, the output comes out to be false. And in this case, in the previous example, it was true because we were able to access all the rooms. Okay. So I hope you understood the input-output explanation. Now let's move to the next slide. Before going to the further slides, let's understand what is depth first search in graph. Okay. So DFS, which is depth first search, is a graph traversal algorithm that explores as far as possible along each branch before backtracking. So in a simple language, in if you remember in tree also there was DFS. What is the simplest and the common difference between a tree and graph is that suppose this is a binary tree, and if you connect it, it is a graph. So a tree has to be unconnected, whereas graph could be connected and unconnected both. Okay. So let me draw a graph. Okay, let this be a graph. I'm trying to draw a directed graph here. Okay, okay, and this one, then will come here. Okay, so I have just this is a random graph which I have drawn. Okay, suppose you started with one. Okay, from one, where you can go to two also, and you can go to three also. Correct. So, but you cannot go twice all simultaneously, right? Into both of the nodes. So what you will do? You will think of going to the two first. So you went to two first. Okay. Then you tried going after from two. Then you tried going more down, more in more depth, but you were not able to because the arrow was pointing in different direction. Since it is a directed graph. So what you did from one to two you went. Then you came back. Then you went to three. Okay. I will write it this way. You came to three. Then you could see that from three you can go to five also, right? So you came to five. From five you cannot go to four because the direction is this way. But from five you could go to six. So you came here. After that, you saw that you cannot go anywhere else because it is the end. So you came back. That is the backtracking part. Okay. And if you could see, explores as far as possible along each branch. Okay. Basically going to the depth. So we went to the depth. Then you came back, backtracking. After that, you could see that you cannot access four or five. Right? So what you do, usually if you remember, we draw a for loop to go to each and every node. One was visited, then two was also visited, three was also visited, five was also visited, six was also visited. It was the four which was not visited. So when we go through a for loop, which basically goes from zero to n nodes, and we mark everyone visited, right? So when you come to four, you say it is not visited, so you keep it as four here. Okay. But you cannot go to five because it is already visited, and two because it is already visited. So this is what a depth first search looks like. Okay. And how it works in a theoretical manner, if you could see, we start with the source node. It could be anything. It could be two also, it could be three also, right? But I started with one. We mark it as visited, visit one unvisited neighbor recursively or using a stack. So this is not necessary. Recursively, when we use, it already uses a stack space. Okay, that's the thing. And we mark it as visited so that we don't visit one node again and again. We backtrack when no unvisited neighbors remain. If you can see, there are two cases when you backtrack. One is that you reach the end, or one, for example, if it was a circular, suppose it was a circular graph. Okay, suppose I am marking with this yellow mark. Okay, the latest mark. Suppose instead of going after five, we are going to four, and we are going to two, and not this one. Let's take it as this. Okay, so the path now is this way. Okay, it's circular one. So when you start with one, when you go to three, when you go to five, then you go to four, then you go to two, then when you come to one, you see that one is already visited, right? So you go back. So this is another case when you backtrack. Okay, the two cases I told you. And DFS can be implemented using recursion. Okay, and this is not necessary explicitly stacked. It was it's an uncommon practice, but I just have written here that if you want to use, you can do it. And why is it efficient? The time complexity comes out to be V plus E. V means vertices, E means edges. What are the edges? These are the edges. What are vertices? These are the vertices which are also called as nodes. And each node and edge is visited once. Okay. Therefore, the time complexity for comes out to be V plus E. V means for each vertex, you might go to n number of edges, right? And space complexity is OV of O vertices because we store number of vertices in the array. Okay, we don't store the edges also. That is not possible. And for recursion stack or visited array. Okay, and it is efficient for graph traversals where full exploration is needed. As you can see, we needed a full exploration in this case, and solving problems that require backtracking or component discoveries. The component discoveries, I will get a question ahead, then we'll look at it. Now, where we can use this DFS? Okay, I've written some of the question examples and topics where you can use. Suppose if you get a question which is related to connected component detections, okay, like in undirected graph, DFS can be find and label all disconnected components. Disconnect components are basically, suppose this is a graph, this is another graph, this is another graph. So there are three disconnected components, but they are a single graph, but all are disconnected. Okay, so output for this particular will be three. So in this case, we will use DFS, not BFS. It is not much helpful in that case. Or in the cycle detection, also you could use that. Suppose if the graph has a cycle or not. Okay, this is a cycle, correct? And you could find the questions in for directed graph, for undirected graph, right? And topological sort is the DAG. So when you have to check for a DAG means what? Directed acyclic graph. This stands for DAG. Fine. Directed means you have an arrow only in one direction, not both directions. Acyclic, it does not contain the cyclic. Suppose this. This does not contain a cycle, right? So this is what a DAG is. So if you have to look for a DAG, whether a graph is a DAG or in question related to the DAG, then in that case you have to study about topological sort and use that concept there. Okay. Path finding without weights, when you have to find a path in a given graph, okay, like solving maze-like problems, okay, without weights, and there could be also a path finding with weights, fine. Solving puzzles like Sudoku and coins and all that stuff. Breach and articulation point detection. In networks, DFS helps identify critical connections, so removal disconnects the graph. So basically, if you have to look for articulation points and you have to remove that, or the bridge you have to remove that, in that case, we use this concept, or we use the DFS in that case. We will follow up with this all these questions as per our sheet. And strongly connected components. Like for example, if you could look at Kosarazu's and Target's algorithms, both uses DFS to find SCCS is in directed graph. Strongly connected components are the components which cannot be break into multiple pieces, right? Okay. So I hope you understood the depth first search in detail. I have not gone in much more depth because it is not necessary. Because if you are studying graph, you should already know about this topic. But yeah, I have figured out some of the things of DFS which will help you in solving the problems. Now let's move to the next slide. To understand what a problem was asking, we should build up an intuition to the problem. Let's start by understanding the goal. So we are given a list of rooms, okay, or list named as room, where each index I represents a room and rooms I contains key to the other rooms, which basically means this is the array which is given to us, and it's saying that each index. So it is a 2D array, 2D list. Okay, it has the index one, it has the index two, it has the index three. Correct. So which is said that each index I represents a room. So this becomes a room, as you understood in the input-output explanation. And rooms of I, which means this. When you do rooms of I of a 2D array, you get this, okay? And when you do rooms of I of j or something, you get the value of this particular thing, which is the key. Fine. All rooms are initially locked except room 0. We have to always start with room 0 and it is always open, which is unlocked and accessible at the start itself. Okay, this is given to us. So our goal is to determine whether we can visit every room by using the keys we collect as we explore. This is understand. So what we could do, each time we enter a room, we could pick up all the keys available there and attempt to use them to access more rooms. We can do that, or we have to do that actually. So we can simulate this using the depth first search. Because why we are using depth first search in this case? Because if you can see, we are not going level wise. First of all, okay, we have to go level one, then level two. No, we are going in the depth because you get a key. Suppose you're walking in a cave. Okay, if this is a cave, okay, this is the entrance of the cave. Okay, and this is another part of the cave. You go come here, and this is another part of the cave. You might go here, and or you might go straight. Okay, so what happens here? Then you get another cave in this part. Then there are more caves here, okay? It's sub caves basically, right? So what do? You come here, you have the key for this, right? You entered. Then you find, okay, I have the path to these particular things, but I have keys only for these two. Okay. Then you go inside this, and you search this complete cave. Then you come back. Okay. Then since you had the key of this, and it could happen that in this particular line of cave, you might find the key for this particular cave also, right? So, for example, you got the key for this particular cave. Okay. You came back. You went in this particular cave. You searched everything. Then you came back. So you could see that we are going in the depth. Okay. Then again we came back, and since you got the key for this particular cave in this line, so you went here also. So this is the way. From here you can understand we will be using DFS recursively to visit the rooms, ensuring that each room is visited only once. Okay, so we need something to keep track of. If we are able to visit all n rooms starting from room 0, we return true, otherwise we return false. Okay, this is understandable, and we figure out that since this question is related to the DFS, we need DFS to solve this particular problem. Now let's visualize the process. Okay, I will try to take an example first of all. Let it be 1 comma 3. I guess then it was 1 comma 0 comma 3. Then let it be 2 only. Let it be 0. That's all. Okay. So we understood that this represents rooms. So this is room 0, which for which you already have the key to enter. This is the room 1. This is the room 2. This is the room 3. Okay. So let's start this way. So it is the room 0. You're standing here, room 0. You have the keys of 1 and 3 with you. Fine. Which means you might go to this room, which is room number 1. You can also go to room number 3. Fine. So you thought of going to room number 1 first. When you reached at room number 1, you saw that you're standing here. Okay, you're standing here. You have the keys of room 1, comma 0, comma 3. Okay. So from here you could see that okay, you can come back again to the room number 0. You could stay in the same room, or you could go to the room number 3. So from here there is a key to room number 3. Fine. So what you did, since we are using depth first search, from here you came to room number 3 first. Okay. Now we are standing in this particular room. Now in this room, room number 3, we have the key to room number 0, which means from 0 to 0 you can go. But since you already have the key to room number 0, it is not necessary, but yeah, you have the key here. Right. Now, where is room number 2? Suppose let the room number 2 be here, but you are not able to access this particular room, right? For entering this particular room, you might have to come from somewhere else and enter here, right? So this is disconnected component in the given graph. So in the given graph, we have actually two components. And what our question says is that if you enter from room number 0, then you should be able to visit all the nodes, which means there should not be not disconnected graph. So it should not be a disconnected graph, and only one component should be there, which means only one component should be there of the graph. So from here, I think you might have figured out what we are trying to solve here. Let me read out the theory. If we visit a room, this is the same thing I explained. We mark it as visited because, of course, we are in a graph and we don't want to visit the same room again and again. So we try to mark them as visited. So since we started with 0, visited, and then we came here, visited, right? So we then don't visit it again. As we traverse each node, we follow its adjacency list to continue the DFS. This is the concept of DFS. We know that. If the DFS completes and we only found the DFS once, that means the entire graph is connected from room 0. So what it says that we initiated the DFS once. If you remember, when we call a DFS, generally, what we do, we use a while loop, no, not a while loop, for equals to 0 to n, which is basically the nodes, right? We have to traverse every node. We check if it is visited or not. If it is not visited, we go to that particular node, and suppose we started from here, it was not visited, then we call the DFS somewhere here, and then recursively we call the DFS in the DFS function, of course, and we go in depth, right? We use the DFS concept fully here. But what happens is that since here, if you start a DFS, you will run it once, right? Since you won't be able to visit this particular node, when you will come back, we will of course increase the count plus 1 because you did the DFS call one time. Then for loop will go again from 0 visited, 1 visited, 2 not visited. So the DFS call will be called again from the source node as 2, right? So because of that, you will run the DFS here and you will come back and the count will increase to 2. And then we will check, okay, since count is 2, it means that there are two components and it is a disconnected graph. So therefore, we were not able to visit every room from starting from the initial room 0. So this is what it is written here. We have only initiated the DFS once, right? That is the thing which I explained here now. Fine. How we can simulate this? We create an adjacency list from the given room's input. Though in this case, it's technically redundant since rooms already act like as one. Fine. We'll just try to create a adjacency list out of it first, right? So that we get a proper adjacency list to run off, which will be basically a directed one. Okay. Then we maintain a visited array. Of course, we need a visited array so that we will initialize it with 0 because it was already visited because it is the starting point. We iterate to the rooms, initiate DFS only when a room hasn't been visited. Every time we initiate new DFS from an unvisited room, suppose DFS function you called initially, fine. Uh, if not visited the node, okay. This is the for loop from 0 to n, okay. So this is done. So in the DFS function, we will have something parameters here. What we will do? We'll do what? We will visit this particular node as one, which is basically true. Then we will go to its adjacency nodes, correct? Then if that is not visited, this particular node, we call the DFS again, right? So that it could go in more depth. So that is what it is written here. Every time we initiate a new DFS, we increment a count CNT, which is basically be a counter. This is written for this particular case. Since this DFS initially initiated, this DFS call is done. We come back when we increment the count. If count becomes more than 1, it means that disconnected component and that it is unreachable and we return false. So what we do, count greater than 1, we directly return false. We don't go any further. The entire graph is connected, the count will be exactly 1 and we return true. Fine. What we figured out, the DFS traversal from room 0 effectively gathers all reachable keys and explore all possible rooms, which means that using DFS was the correct approach. If the number of DFS initiates count is more than 1, it implies that we all the rooms are accessible from room 0. So we understood the concept of or we understood the hidden concept that we have to basically look for the disconnected components. Therefore, we use DFS. Okay, and this method ensures we don't visit rooms accurately. So this all of the three things helps us along with the visited array that this method ensures we don't revisit rooms and accurately detects whether all rooms are visited using the available keys, right? So I hope you understood the intuition. Now let's move to the next slide. Now since we got the intuition of the problem, let's look into the approach how we're going to solve it. Let's start with step 1. Handle base case and initial conditions. Okay, what is the base case here? If the input list is room is empty, suppose the room which is given to you, if n equals to 0, just return, man. Nothing to do, right? It will be returned true because no rooms are visited. So there is only one component, you could say, and that's all. We define n as the number of rooms and create adjacency list, which is named at ADJ, to represent which rooms are reachable from each room. So basically, what we do, we try to traverse the given array from 0 to whatever it is. Then what we do, we pick up each node. What we do, adjacency of u dot append v, which means u will go to v. Correct? We create this graph similarly from again u to v, u to v. That's all. Even though rooms of I itself is sufficient, forming adjacency allows us to follow a standard graph traversal. Now you will be thinking why we are creating the graph again if it is given to us, right? Because rooms of I itself is sufficient, but forming adjacency graph allows us to follow a standard graph traversal template and emphasize the connectivity structure. So this makes the question much more clear and much more easier to understand, right? The problem which we're trying to solve. And we also create a visited list of size n initialized to 0, which is unvisited. Basically, we will create a visited array or list and we will initialize everything to 0, which means none of the nodes have been visited till now. Okay. And to keep the track of each room, we have visited already. That's all. Now, in the step 2, as I said, we iterate through each room from 0 to n minus 1. For how to iterate? 0 to n minus 1. Please keep in mind we have to iterate a graph to visit every node. Otherwise, we won't be able to start with any of the nodes, right? Until and unless it is necessary. Otherwise, you could also directly call DFS without using this particular for loop. If you know that the component, the graph which is given to us is one single component, if you already know that and you just have to do a DFS traversal, you can directly call a DFS function from a source node. That's all. But if you are unsure that a graph might be unconnected or disconnected also, then in that case we need a for loop so that we can, you know, take a hand in all of the particular nodes given to us. Okay, or we can cover all the disconnected components. For every room not yet visited, we increment a counter and start DFS from that room. This is the initial condition if you remember after the for loop. If at any point count is greater than 1, we return false immediately because there is no use of going any more further for the other components because it is not able to visit all the rooms from the starting source which is 0, right? In step 3, we perform the DFS to reachable room. This is basically the DFS function. The DFS function takes the current node. The DFS function takes the current node, let it be node, I'm writing a node. It takes the visited array and it takes the adjacency list with it, right? And this will be the current node every time. Every time you call the DFS, the current node will be passed here. On entering this function, what we do? We do visited of node, the current node is 1 because you visited this node, right? Then you iterate, then you go to the adjacency part of this particular node. Suppose there is a node 2 and it is connected to multiple nodes, right? 3, 4, 5, whatever it is. So you need to visit all of this, right? For that, what to do? For child, let it be child in adjacency of node. So if you write adjacency of node, what do you get? It's simply like if 2 is there, so adjacency nodes are 3, 4, 5, right? So you are traversing this now. And if that is not visited, child, you call the DFS again and you pass the child here and other parameters. So this child goes up and again it becomes a current node. And when you go in the depth of this 3, if 3 is there and it has 6, 7 connected to it, then you go and traverse 6 and 7. Then you iterate back, then you go to 4. This is the way the DFS works, right? This is what is written here. And at the final step, which is step 4, we return the result. You know that after a DFS call, which was initially called within the main function, this is a function call. Here, this is a function call, right? Not the definition. One time if it is called, and if it is called another time and count becomes 2, which means we are going in another component of the graph, we immediately return. Because what is the use of going and checking for other components when we need only the component should be 1, or only when we need a component should be of 1, count 1, right? Let's try count greater than 1, we return false. So I hope you understood the approach explanation. It was pretty easy and straightforward. Now let's move to the next slide. The code is the exact copy of the approach we discussed. Let's understand it line by line. So this is the function which is basically given to us, fine, but can visit all rooms. So this is the length taken by the rooms of the rooms. This is the adjacency list which we create. Okay, this particularly means that I, whatever the value of I is connected to well. Fine, this is the thing which is happening here. We create a visited array or list, initialize with 0, count also. Now, this is the one which I was talking about for iterating in the given range so that we can go for every nodes. If it is not visited, we increase the count. Okay, we are starting with the first component. We call the DFS function. It comes here, makes it visited. Then we go for the adjacency nodes of that particular current node and do the same thing. When this is done, we come back. Since count is 1, no nothing to do. Okay. When you go back, If count becomes 2, you call the function, then you come back, you say that count is 2. So we return false. Otherwise, we return true. Therefore, the time complexity for this becomes n plus e. N means nodes, n number of nodes. E means edges, right? It is not n cross e. Please keep in mind, it is n plus e. Because for each nodes, you are traversing the edges. You're just traversing, right? You are not multiplying it or multiple times you're going for it. Also, to make it more clear, let me tell you one more thing. The loop which we are taking of the adjacency list runs O of e times. Okay, this one. Let me use another pen. This particular loop, fine. And since we are visiting each key exactly once, it becomes this. The DFS traversal, this one, visits every room once and explores each key, which is the edge, once, right? So it takes n plus e in total. They're not coming to a particular node which is already visited multiple times. Therefore, the time complexity would have been n cross n if we are visiting the particular node multiple times. But here we are visiting it once, therefore it is n plus e. Okay. And space complexity is also n plus e because we are creating an adjacency list of size n plus e, pretty straight and forward. N is node, E is edges, and O of n for the visited array. So together they comes out to be O of n plus e. So this is what a code explanation and time and space complexity is all about. I hope you understood it. Now let's move to the next slide. Now, since we have the understanding of the code, let's look at the dry run of the example. To make the dry run much easier, I have already brought the code here. Okay, let's draw the graph first. This is 0, this is 1, this is 2, this is 3, this is 4, this is 5. Okay, this is 6, this is 7. Okay, let's do it. So this is a node 0, for example. Okay, I will mark it as this is node 0. Fine. It has a key to node 1 and node 2. Okay, and node 1 has the key to node 3. Node 2 has the key to node 4. Node 3 has the key to node 5. Then node 4 has the key to node 6. Okay, 4 has the 5 has the key to node 7. So here we will start from here, right? We have created the adjacency list and is taken here. Now this is the graph which we created now. Visited. Let me create a visit array also. Now we start from here and we take the count also to be 0 now. So for of I we started from 0, right? And we have the key to it already. If it is not visited, yes, it is not visited. So what we do? We increase the count to 1. Then we call the DFS function. We send 0 here. So here we have 0 visited array and the adjacency list, right? Please focus on the 0 part. Now you make this node true. It is visited. Then you go for its adjacency part, and if it is not visited, suppose we go to the 1, right? And it is not visited, right? So we call it again from this particular node. We come back here. This becomes 1 now. So we make this one visited. Again, we go to the adjacency node of the current node, which is 1, fine. And if it is not, that is not visited. So here we only have 3. So we call again, now it is 3 what? Okay. So we make the node 3 visited. Then again we go to the adjacency list of 3. Again so it is 5 here. If you can, we were standing here, now it's 5, right? So I will cut this. Now this current node is 5, and we mark that also visited. And then we go to its adjacency list, and in that we can see we have only 7, and it is also not visited in the array. So we call it. So instead of 5, now we have 7 as the current. We mark it as visited. After that, we try to go for the adjacency of that particular node. Since it has nothing, no more DFS is called. We go back, we go back, we go back, then we come to 0 again because it is backtracking. Okay. Now let's come to the part where the current node was 0. And since if you see, we go to the adjacency again, we see it is not visited. If we go to the left first, we see one is visited right here. So we cannot go there. Then it checks to the another adjacency node, which is 2. We see it is not visited, so we call for it, and the current node becomes 2, and it becomes visited here. Again, we go and we see its adjacency list. We check it is 4 right here. It is 4. So we call it. So instead of 2 now, current node is 4. We mark it as visited. Then we go for the adjacency of 4, which is only 6 in this case. And it is also not visited, if you can see the array. When we call for that, now the current node becomes 6 here. Then we mark it as visited. Then we try to go for its adjacency list. But since it does not have anything, we track back again. Okay. Now if you see, we cannot go left also, we cannot go right also. So we come out of this particular loop we called here. We check if the count is greater than 1. It is not, it is only 1. Then we go back to the for loop. Since it started with 0, it is visited. 1, visited. 2, visited. If you can see, right, all the nodes from 0 to n are visited. So it never goes out of this particular case. It does not go in the if case, if you can see that. So DFS is not called anymore time. So we return true at the end. So I hope you understood the dry run. It was pretty simple and straightforward. If you have any doubts or confusion about the solution we arrived at and how we arrived at it, I suggest going back and understanding the intuition, the DFS concept if you don't know anything about that, or the brush of the thing, the approach and the code. After that, do a dry run by yourself and 2 3 examples, and I'm pretty sure you will understand both the solution and the thought process behind it. Now let's move to the next slide. Now, since you're familiar with the problem and the solution, let's move to the lead code and code the solution. Okay, let's start. Let's take n equals to length of the rooms. Then we will create an adjacency list. This is the 1D list. This makes up to the 2D list. If you don't know about that, then what we do for in range of n. So if you are confused about how this particular thing works, it is like suppose this is 0, 1, 2, 3, right? These are the nodes, n size. Fine. For this each n, you allocate space this way. Right? So these are the thing where you store this connectivity or the adjacency list, which we call. So this list is used for that. Okay. So for I in range, we create this, fine, this particular left hand side part, and this array creates a size of n, or you could say dynamic list, which can store the value, right? This way. Okay. So I hope you understood this. Okay. Now for I in range, this will take the rooms, fine. And for val in rooms of I, it will take the keys of in storing in that particular rooms, fine. So adjacency of I, this is the room. This can go to this particular, having this particular key, so it can go to this particular node. Fine. This is what we did here. Now we create a visited array of size n, where we have initialized it with 0, means unvisited. With the count equals to 0, for I in range n, if not visited, we increase the count. We call the DFS, we pass the node visited array and the adjacency list. If count is greater than 1, we return false, else we return true. Fine. Let's code the DFS. That's a pretty simple one, which will have these parameters: node, visited, and adjacency list. So if you remember, we mark it as visited now. Visited of the particular node. Okay, so we visited this node, we marked it here. Then for val in adjacency of that particular node. So we go to the adjacency list of the particular node, and if not visited, we call the DFS with that particular child node, you could say, or the adjacency nodes. Okay, that's all. Then let's try submitting it for the sample test cases. Okay, now finally submit the solution. Okay, so we have successfully submitted our solution. Now the code of the problem is available in my GitHub repository. You can find the link in the description. Thank you, everyone.